So part 2, we need to find the final conditions, and so we're going to assume time is large enough such that steady state applies. So we'll assume it goes to infinity and draw the equivalent circuit. So again, 2 ohm is in parallel with the capacitor at steady state. Looks like an open circuit, but now the 10 ohm resistor is shorted by the switch. The inductor looks like a short, and that's connected to the 24 volt voltage source, and the current through the inductor is given as I infinity is right there, which is also the current through the 2 ohm resistor in this case. So we can find I infinity is just being the current through the 2 ohm resistor with 24 volts across it. In other words, 12 amps. And the voltage across the capacitor is the voltage across that 2 ohm resistor, which is 24 volts by inspection. Okay, so just as a reminder, we found so far I0 plus is being, let's see what, as 2 amps, and I infinity as 12 amps. So we're going to see that that current increases. We've seen V0 plus is 4 volts, and V infinity is 24 volts, so that voltage is going to increase. And we still need to find the first derivative of I at its initial point following the switching event, as well as the first derivative of the voltage across the capacitor. So how do we do that? Well, we need to examine the circuit when under the non-transient condition, or the non-steady state condition, the transient condition, in other words, at t equals 0 plus seconds. So note the difference between this and t0 minus, because at 0 minus we can assume it's steady state and the circuit gets simplified. At t0 plus, it's the instant after the switch closes, and the circuit immediately goes into transient mode. So we have a 2 ohm resistor in parallel with a capacitor. We can't get rid of that capacitor here. It's not steady state anymore. That's 1 over 20F, and this is V at 0 plus. Now we know what that initial voltage is. We just don't know what the initial derivative is, so the initial rate of change. Likewise for the inductor, that is 0.4 henries, we know the initial current through the inductor, but we don't know what the first derivative of that current is. And remember, the first derivatives are necessary because we have a second order system, so we're going to have to get rid of the boundary conditions of that first derivative term. So the way I always remember this is I like to remember, I look at the problem each time in a unique way based on what we're trying to solve. So in the first case, we need to find the first derivative of the voltage, for example. So let's think about where the first derivative of the voltage is going to appear mathematically. And we can recall that for a capacitor, IC equals C times dVc dt. So that's the dV dt term comes in when we're describing the current through a capacitor. Currents appear with KCL, so we're going to use a KCL expression in order to describe the currents through each of our branches in order to get the dV term. So KCL at, if I define the bottom node as ground, this top node becomes V0 plus. I'm going to do a KCL at V0 plus. So the current through the 2 ohm resistor is V0 plus minus 0 over 2. The current through the capacitor, which is IC, is the capacitance, which is 120, times dV0 plus dt. The current through the inductor is given as V0 plus minus 24. Oops. Excuse me, the current through the inductor is just simply given as I at 0 plus. It's already defined for us, and so I give that a negative sign since it's going into the node. So we have We know what v at time 0 is, and we know what I at time 0 is, so we can solve this for dv dt must equal 0 volts per second when we solve that out. Okay, for the next piece we want di dt at time 0 plus. So recall here that that term shows up in the describing the inductor voltage. So V equals L times di dt. So we're going to want to do a KVL in order to describe the inductor voltage. So let's do a KVL of the rightmost mesh, since that's where the inductor shows up. So I'm going to do the KVL as walking around clockwise. So first I'm going to describe the voltage across the capacitor. So I'm gaining voltage V0 plus as I go from bottom to top. I'm going to lose the voltage across the inductor. Noting that this arrow is actually described as being negative I 0 plus. It's going opposite direction, so it will be negative L di 0 plus dt. And then I lose voltage 24 volts across the voltage source. Okay, then solving this expression for di dt at time 0 plus, I get that is 50 amps per second.